Today I'll present several column curves. When we design the column, we need the column strength curve. So I'd like to introduce the CLC column curve first, and then SSRC. And I'll show you some design example, ASD, PD, LRFT. This is the scope of the lecture at this week. So when you develop the CLC column curve, we consider residual stress. You must know residual stress, right? And then geometry imperfection is not considered. From this assumption, we drive the CRC column curve. CRC means column research council. From this CRC column curve, ASD column strength curve and plastic design PD column strength curve are driven. And then another column curve is SSRC. SSRC stands for Structural Stability Research Council. This SSRC developed its own column curve. It is called SSRC column curve. So SSRC column curve consider residual stress and geometric imperfection as well. From this SSRC curve, LRFD has been driven. Okay, and then finally, I will compare this design example using ASD, PD, LRFD column curve. That is the whole story of this week. So to get the column curve of idealized steel eye section. Meaning of idealized steel eye section is we neglect web. We just consider flange only. Why we neglect web? It is for simplicity. As you know, in this flange, we have residual stresses, right? Due to uneven cooling. So sigma RC means compressive residual stresses. Sigma RT is tensile residual stresses. These residual stresses are self-balanced stresses. Okay? So sigma RC and sigma RT, the magnitude of those are equal to sigma R. We have another residual stresses here at this flange. Now we are considering inelastic column. The PCR at elastic column is just Euler buckling load, right? Pi square EI over KL square. It is elastic column. But here, as you see, EI, EFF. EFF means effective. Because in the inelastic column, only elastic core works. Inelastic portion of the section cannot sustain any more load. So this elastic core provide flexural rigidity against buckling. It is inelastic column. Previously, you remember PCR equal ET over EPE, right? In the case of inelastic column. Last lecture, I explained. Today, instead of ET, we can calculate IE. IE stands for elastic core of I. Then what is elastic core? Let's look at this. This is the stress state. You see here it is compressive residual stresses, right? Tensile residual stresses at this flange. So we draw this stress state. This dot line. This part is compressive residual stresses. This is tensile residual stresses. And then if P increase, this compressive part yield first. This part is already yielding like that. The stress is sigma y. Also this part, the stress is sigma y. Okay, due to P increase. How about this red part? What is stress state? This red part is not yielded now because the stress is not sigma y. Because this part, the stress is that is stress. So this red part, the stress state is elastic. So we call it the elastic core. This red part is elastic core. In here, PCR equal pi square E IE. IE means elastic core because this blue part does not have any fractional rigidity because it is already yielding. So in this inelastic column, PCR can be written in this form, pi square E IE. This IE is elastic core of I. Okay, then let's calculate the ratio of IE of I. What is I? Firstly, this one, this flange, I. How to calculate? So I is I0 sigma A Y square. Okay? That is the equation. So I0 is along this axis, we can calculate I, but the thickness is very thin, so it can be negligible. Plus area times y square. What is this area? This is BF and thickness TF. BF TF. This BF TF. And then we have to move this y. Okay? This y equal h over 2, right? Approximately h over 2 square. So h square over 4. 1, 2. So this 2. We can write in this form. And then IE, that means the moment of inertia of elastic core. So elastic core is this red part, right? Then BFE. Area is BFE. PF identical. And then h square of 4. The distance is identical. So like that. So if we cancel out these things, the remaining one is BFE over BF. So PCR can be written again BFE over BF. PE, that is the buckling strength, buckling load of inelastic column equation. Do you know the value of BFE? You don't know because you don't know sigma 0 something. The distance from here to here is sigma 0. So you don't know that one. So we need express BFE over BF as the stress term. So from now on, we calculate, we establish some equations to show the stress term instead of BFE over BF. Yeah, P applied here. So you can calculate the equilibrium equation. P times, you can express in terms of stress. So total stress here, then sigma y BF TF. That is total stress. In fact, that is elastic core. So you have to deduce the force of this part. How to calculate this one? The area of this part is BFE, and then this TF. That is area. BF TFE. So it means this part. And then we have to calculate average stress of this part. What is average stress of this part? If we assign this stress is sigma 0, then this height is sigma y minus sigma 0. So average stress is 1 over 2 sigma y sigma 0. So in order to calculate the force from that the stress state, we calculate the total assuming sigma y applied, and then times the total area minus this part. Okay, this part, because this part is not yielding part. So we deduce that part. We can establish this equation, equation 2. And then from this geometry, we can establish this equation. Sigma y, sigma 0, sigma y, sigma 0. This height, right? Then this one, okay? BFE over 2. Proportional the relationship. And then we calculate here. This is sigma y, sigma r. This height is 2 sigma r. That the proportional distance is this one. So BF over 2. Proportional relationship. So from this equation, you can write down this equation. So you have equation 1, 2, 3. Now you input equation 3 into equation 2 because here sigma y, sigma 0. So you input this one here, then you can write down like this. BF times 2, that is A. So A. Okay, remaining one is sigma y, sigma r, BF E, BF square. You get this equation and go to the next page. If we let sigma AV equal P of A, that means if we move this A to left hand side, that is sigma AV. Average stress, that means average stress, that is AV. And then you move sigma Y, move sigma left hand side, then you can get the equation BFE over BF. That is equation 4. If we input equation 4 into equation 1, equation 1 is this one, BFE, BF. So you get the equation of this term. So if we input that one, this term, then you can write PCR equals sigma y, sigma AV, sigma r, PE. Now, divide by A, sigma y in both sides. Then PCR divided by A, what is that? Sigma CR and sigma y. Square root 2, this one. PE divided by A, what is that? Sigma E, okay? Then sigma y. Now, you can express this sigma CR as terms of the stress. This PCR also as terms of stress. You know sigma R, sigma Y, average stress, P over A. That is the PCR of inelastic column. From this equation, if you let lambda C is defined square root sigma Y over sigma E. We let lambda C equal square root sigma Y over sigma E. If you input sigma E, Euler buckling stress. What is Euler buckling stress? Pi square E, KL over R square. That is Euler buckling stress. Do you remember? If you input that Euler buckling stress into here, then you can get lambda C is like this. It is called slenderness parameter. We can rewrite sigma CR, sigma Y relationship using this lambda C. This lambda C, as you see, is the term of square root sigma Y, sigma E. If you compare this term and this term, this is just a reverse relationship. So you can rewrite this equation is like this over lambda C square. That is the regarding strong axis buckling strength relationship. In strong axis, you calculate IE. This I calculate against this strong axis, right? Then if you calculate the weak axis, you have to calculate against this axis. Then in weak axis, this PCR, the equation is identical. IE over IE, IPE. The basic equation is identical regardless of it is strong axis and weak axis. But the calculation of IE and I is different, right? Because here, weak axis, this is weak axis. You have to calculate the I against this axis, right? So how to calculate? That is BF. That is TF. You can calculate of I. What is that? TF, BF cube, okay? Divide by 12. You have 2. 1, 2. So 2. Now that is this one. This IE is, we have to consider the elastic core. This part. This one is BFE. Okay, that elastic core part. Then you can calculate again. TF BF cube over 12. Then you can write as this simple form. Like that. Delete something like that. Referring to the result of the strong axis, you can write the weak axis result like that because this cube here, so you add here cube for weak axis. Do you understand? It is elastic column or inelastic column. Inelastic column. Okay, so we derive inelastic column equation from this one and this one. This is a strong axis. This is a weak axis. If sigma r equal 0.3 sigma y. We input here. When average stress buckling occur, so we can let sigma CR equal sigma AV. We are interested in the buckling state. So this average stress must be buckling stress. So must be identical. So this one identical. Sigma R equal this one. So we can draw P over Py versus lambda C is this one. P over Py means if we multiply A, here A, then this is Py, this is P. Then we can draw the relationship of P over Pi versus lambda C using this equation. Let's look at the curve P over Py and the lambda C curve. This is some fringe. We assume the residual stress is like that. So this is a linear residual stress relationship. In that case, we can draw this number 2. This line, you see? This line. You see here 0.7. From here, the elastic. This left-hand side is inelastic. Why 0.7? Because residual stress is 0.3 sigma y. So that is 0.7. If weak axis case, we have some equation for weak axis. So if we draw the curve using that equation, like that, this number 4. Then what is that parabola? That means residual stress shape is not straight. That is curved like that. If we assume the residual stresses distribution is parabola, then we get the curve number 1 for strong axis. Okay? Regarding weak axis, we get number 3 like that. That line. So basically now we calculate up to here. This is inelastic column. Number 1, 2, 3, 4. Regarding strong axis, 1 to strong axis, 3, 4 weak axis. That is the residual stresses distribution. Parabolic, linear, parabolic, linear. So we get 4 different column curve, inelastic column curve. So we derive those equations. Let's look at the CRC column curve. So far we just some study general inelastic column and their curve. But from now on, I would like to introduce this CRC column research council curve. In this CRC, some inelastic column assume this curve. Okay, sigma CR equal A minus B KL over R square. We assume like that. Some inelastic part from here to here. It is ultimately CRC column curve. So we the study how that CRC column curve has been driven. So firstly, we assume this curve equation is this. So A minus B, A and B is unknown. So using some boundary condition, we can calculate A and B. Let's look at slenderness ratio. If slenderness ratio is 0, that means this point, okay? If slenderness ratio is 0, what is the strength? Sigma CR. Buckling stress is K over R equal 0 means this term is 0. Eliminate. So sigma CR equal A. So sigma CR equal sigma Y because the length is 0. So it will be failed by yielding this point. And then we consider previous derivation. We assume the residual stresses is 0.3 sigma Y. But the derivation of CRC column curve 0.5 sigma Y is used for sigma R. Okay? For conservative, we consider some more larger residual stresses. It is a safe direction for conservative direction. So sigma CR equal pi square EA KL over R. What is this? Euler buckling stress, right? So Euler buckling stress is this curve. Euler buckling stress is always some unique, identical. So residual stresses, as I mentioned, is assumed 0.5 sigma y. For this point is the boundary between elastic and inelastic, right? So we have to know this value. We call it CC. We have to calculate this CC. So as you see, this Euler buckling stress is 0.5 sigma y. From that equation, we can get the CC value. Here, sigma CR pi scale Euler buckling stress is equal to 0.5 sigma y. Then you can calculate slenderness ratio from this equation is this one. It is called CC. So this point is CC. It is just a boundary between elastic and inelastic column. CC value again is this one. So we get this value from Euler buckling stress. So Euler buckling stress is elastic column. This is elastic column. So we are currently calculate inelastic column. So you see this is the inelastic column curve. So sigma CR equals sigma y minus b, something like that. Okay, because A is already, we know this value, sigma y. So this one equal 0.5 sigma y. From this equation, you get B equal this value. So you get the boundary A from this value, B from this value, from this inelastic column, both boundary condition. So sigma y minus b KL over R square, KL over R square. So you input this boundary value of KL over R. So you input this value, this point. That point stress is 0.y. That is the relationship, 0.y. From this boundary, you can calculate B equal this value. So now you get the value of A and B. So sigma CR can be written in this form. This is B, A, and this is B. KL over L square like that. That is the CRC column curve. If you use this CC, what is CC? This one, okay? Square root 2 pi square E sigma y. So instead of this one, you can use this term. Then sigma CR equals sigma y 1 minus ECC square KL over R square like that. Do you understand? So it is inelastic column region. From here to here, from here to right hand side is Euler buckling stress. That is CRC column curve equation. If we express using lambda c square slenderness parameter, this is lambda c. If we use this relationship, then you can write down this equation from here to here, from here to here. That is the CRC column curve. See you in the next lecture. Bye.